Alaikum and hello everyone, my name is Mohammad Fayaz Islam and today I will present my final term OBE assignment for the Digital Logic Circuit course. The focus of the project is design and implementation of automated digital parking control system. The objective was to design a system for a garage that can house a specific number of cars. Based on the variable derived from my student ID, the maximum capacity of the design is set to 11 cars. The system requirements are specific. We use entry and exit sensor to track vehicle flow. When the garage reaches 11 car, it must display static full signal, otherwise it show a blink space available signal. The design incorporates 555 timer for the display, counters for tracking and FSM for timing operations. Here is the high-level block diagram of the proposed system. As you can see, the core of the system is the up-down counter, which receive input from entry and exit sensor. The counter's input is fed into a comparator. This comparator checks the current count against our maximum capacity. If the counter equals the maximum, it triggers the monostable circuit to drive the full display. If the counter is less than maximum, it triggers the astable circuit to drive the space available display. We also utilize an encoder and register for the key input. Moving to the flow diagram, we visualize the logic process. The system continuously monitors the sensors. When a car enters, the counter increments. When a car leaves, the counter decrements. This 4-bit counter value is constantly compared against the fixed maximum value of 11 cars. This discussion block determines whenever the 7-segment display shows the static warning or the blinking availability signal. To implement the counting mechanism, I designed a synchronous counter using JK flip-flop. On this slide, we can see the state transition table. I mapped the decimal state from 0 to 11 and determining necessary next state logic for both counting up and counting down. Using this transition, I perform K-map signification to derive the excitation equation for the flip-flop. For example, the equation for J3 was derived as Q1, Q2, Q3. This equation dictate how the flip-flop count to from the 4-bit counter. Here we have the circuit schematic for the display counter. This compares the counter output with the reference limit B comparator unit. Monostable circuit shows on the left the 555 timer configuration handles the static full signal. A stable circuit shown on the right. This generates the square wave required to make the space available signal blink. I selected capacity values of 50 microfarad to ensure timing stability. Precise timing was required for the blinking effect. Using my ID variables, I calculate the following parameters. P equal to 50 and frequency is 12 Hz. Duty cycle is 50 50%. This result in the high time and low time of approximately 41.5 millisecond each. To achieve this timing, I evaluated three capacitor options: 50 microfarad, 250 microfarad and 470 microfarad. 50 microfarad is required a resistor value that was too high, 1200 ohm, and the required resistor value that too low in 47 microfarad is 127 ohm, which risks causes an overflow of current in the circuit. But 250 microfarad, this option is provide the optimal balance. Therefore, I selected 250 microfarad capacitor. It allows for a resistor value of roughly 240 ohm, which avoid the high resistance of the smaller capacitor, which ensure a stable current supply compared to the larger option. For the control logic, I developed a finite state machine FSM. Due to the specific constraints of the assignment, the timing was normalized to Th equal to 4 microsecond and TL equal to 4 microsecond. The state diagram shown here illustrates the transition between state to procedure, the output A for the high duration, B for the low duration, effectively create the required pulse pattern. The logic was translated into a Verilog HDL code. The module takes a clock input and drives output A and B. I utilize 3-bit register to manage the states. The code uses assign statements and non-blocking assignments to ensure synchronous operation of the FSM at every positive clock edge. To conclude, I apologized limitation of specific design. Capacity limit. The use of 4-bit counter limit maximum count to 15, while sufficient for the 11-car project. It would need expansion for larger garages. Fixed frequency. The blinking rate is hard, weird. Adding a potentiometer would allow the frequency to adjustable. Stability. The 555 timer is a sensitive to temperature, which could cause slightly timing inaccuracy. Despite this limitation, the system successfully meet all design requirements for the assigned problem. Thank you for the time.